So today's lesson's on acceleration time graphs. I'm going to begin right now, so please end your conversations. Remember, there's only 3 things that you can do with a graph. The first one is very obvious. Read the graph, right? So, Mr. Edgington, what does it take to read a graph? What do you need to look at? Good. You need to identify, like, what do the x and y axis even represent? Correct? Yes. Are they relating displacement to time? Are they relating velocity to time? Are they relating acceleration to time? Do you think there will be any other graphs coming your way in the first unit? I mean, that's pretty much it. If you study those 3 and all the way they relate, you should be okay for the first test. Have a look at the scale. Sometimes the scale can be a little bit misleading, so make sure you do a quick double check. You know, is it going up by 0.1s or is it going up by whole units of 1? And then also at that scale, you can check for SD, which stands for, when I hand back your quizzes, sometimes I write SD, significant digits. So take a look there. So also, there's one more thing on a graph that might be new to some of you: direction. I'll just draw one quickly on the whiteboard here. What if you're doing dt like this, and then it's something like this? Guess what? Right here in green at 0, that's your home base. That's where you start, home base. That's your reference. Traveling away from the origin. Traveling towards the origin. Oh, I'm back at the origin. Now I'm going away from the origin in the other direction. Okay, so yeah, lots of times you guys are used to seeing graphs just one quadrant only, right? So keep in mind that we will often be going x-axis to the right only, typically, because that's time. You only have like quadrants 1 and 4. Are you above or are you below? You know, in math class they give you all 4, right? So it's actually kind of a break. You only have to deal with 2 of them. So we'll keep going. So other than reading the graph, which I think most of you at this point in your lives, that should be pretty good skill at this point. The next 2, especially slope. Slope is just hammered on in high school. Slope, remember, slope represents rate of change. A rate compares 2 quantities. Could be dollars per hour, could be kilometers per hour, could be dollars per gram if you're buying deli meat at Superstore. It could be any 2 separate units. They have to be different. Okay, so it's like, how much does the y compare to the x? Okay, always y over x. And slope should be pretty well known at this point. Then there's only one other thing that a lot of students will forget about. This third one is calculating the area. I find the students that forget this one are the ones that have done little to none homework, because this one's scattered throughout the first 2 sections, 2.1 and 2.2. So look for some graphing questions, go find some area questions, and you'll be good at this. Remember, it's under the curve to the x-axis. So you can sketch this. I'll get this stuff out of the way. Let's just do something like this. Just keep in mind that there's positive area and there is negative area. Here, I'll zoom in. What's going on with my computer? I zoomed in, but it's not zooming. Lag. Okay, if you look here, the yellow represents positive area and the red represents negative area. Okay, so notice that it's shaded below the curve above the x-axis or above the curve below the x-axis. The zoom feature's not working. That's bizarre. Okay, so today's focus is the acceleration time graph. And this one is not too bad. This is all you're going to be working with. Remember, accelerations could be positive or negative, depending if you're accelerating towards or away. This one here, you don't see too much, and you don't have to worry about this. You'll never have to do the slope of an AT graph. Okay? So remember, if you have a DT graph, how do you get the velocity? Take the slope. And if you have a VT graph, how do you get the acceleration? Take the slope, because slopes represent rates of change. For the first one, for displacement time, you're thinking to yourself, how does the kilometers relate to the hours? Oh, that's a speed. But if you have speed already, how does meters per second relate to second? Oh, that's acceleration. Now what about working backwards? Yeah, you got to take areas to work backwards. If you have AT and you want velocity, take area. If you have VT and you want displacement, take area, and you work backwards. Those two things in calculus are called the derivative for slope and the integral for area, and this is where all this stuff comes from, but of course we sort of just memorize stuff like calculate area. We don't really understand why. Because all this stuff is derived in calculus. Okay, so let's take a look. Calculate the slopes of the three sections. They represent meters per second per second. In other words, acceleration. So these are all done for us. We just have to do a quick scan. Let's do the first section. First of all, what does this formula represent? My pointer, what is that saying? This is the slope equation, right? y2 take away y1, x2 take away x1. Are you guys okay with these two values? So y30, because the second point is 30, and the first point was 18. And that was accomplished in the first 4 seconds. Second point is always written first, the first point. Let's take a look at that acceleration. Not too bad, right? You guys could do that. And you'll only get, for VT calculations to AT, you'll only have, this will always be linear. So you can jot that down. It'll always be linear, no matter what. And then these ones will always be constant, no matter what. Otherwise, it's just a little bit above our pay grade. I like the second part. What do you notice about the second part? Is the y variable changing? And then a lot of people will just jump to conclusions. They'll say, oh, uniform motion. Is that a correct assumption? Yeah. Did they study it? Yeah. Do they understand it? Hopefully. Is the velocity changing? So are they accelerating? No. And then finally, what's happening here? The slope. Originally, this at question 1 here, slope's positive, so this must mean slope is. It just means that whatever the y-axis is, it's decreasing as time progresses. As time progresses, you're decreasing. So what does that mean? You're going 30 meters per second, and then you're going 0. What did you do? Yeah, and you can't just stop in a heartbeat. You have to slow down to a stop, right? Okay, so then here's some language that you can use. And this is just to be careful, like this is what I do. This one's speed up. This one's speed down. To me, that just is very straightforward. You can also use these words. Accelerate. And then this one, decelerate. Those are also used. For some reason, accelerate has 2 C's and decelerate has 1 C. I don't know why. Nothing to do with physics, though. And then this is uniform motion here. And these two are non-uniform motion. And that word uniform, you could use it with velocity, you could use it with acceleration. Uniform just means it stays the same. Okay? Yes, dear.
Why is it, why did, the first one, it says 18 like on the graphics phone.
If you zoom in, I don't know if my thing will zoom in right now.
I mean, even on the paper, it's like up to 20, so I don't know.
It's just a photocopy thing. Like it does that. If I could zoom in on my screen, for some reason it's not letting me.
What about on an exam?
It'll be very clear.
I hope it is.
It will be. Because this is like small PowerPoints that I got so many of them. I don't have the time to like be nitpicky about each slide. But on the exam, I'm very nitpicky about the presentation. So don't you worry. Okay, let's go to the next slide. Next slide. Okay, perfect. So in the last slide, we were relating the VT to the AT, so we had to do slopes. And you can see on the top right here, positive, 0, negative. Okay, you guys see that? Positive, negative, 0. And this acceleration will always be constant. It'll be above, at the x-axis, or below the x-axis. Let's relate this same VT graph, though, to the DT graph. Let's take a look here. So here's the same VT graph. The three sections are treated separately. Areas are calculated as displacement. Understanding uniform motion, non-uniform motion, which are linear and quadratic respectively, and the slopes of tangents, which give you the instantaneous velocity, will help you sketch a position time graph. This is no easy task, and you won't be asked to do this on an exam. You'll only be asked to analyze. So let's look at the first section. See if you can draw in a vertical line that is the area of the first section. Now that's an irregular shape, correct? So what you could do is split this into two sections. Area 1 and area 2. Let's look at area 2. It's just a rectangle. Base times height or length times width. That's right here. Okay, so it goes to 18. You can see on my screen it's slightly below 20. And then it goes over 4. So 18 times 4. Plus the area of A1, which is that triangle up there. And the area of a triangle is 1/2 base times height, or base times height divided by 2. So the base is 4. And the height of this triangle is from the 30 to the 18. That's why they subtract the 30 to the 18. You guys see that? That's the length of the height of that triangle. So totally, this thing's displaced 96 meters positive. It's really important that you include that positive, because you're above the x-axis. So that's section 1. What about section 2? You would have to, just as long as you can read those values, no problem, you would calculate, in this section, top right. So now we're up here. Now we're up here. This is like, look, they're using 29 seconds and 4 seconds. So from 4 to 29, that's the width. And the length is the height of that rectangle, that's 30. So you've displaced another 750. Now if you compare the bottom left position time to the top right position time, how are they different? This one is the quadratic, non-linear, quadratic, right? Non-linear, quadratic. And then this one is linear, straight line. Because here the VT is increasing, so velocity is changing, non-linear DT. Here the VT is constant, VT constant, so position time uniform. constant. You're covering the same amount of distance every time. That's when you're going the same speed. And then if you're going to decrease speed, you should expect nonlinear. Okay, and then the last calculation, again, you guys could do this on your own. If it was a little bit more zoomed in, you would just calculate the area of that triangle, which is down here in that corner. Okay? I think most people are good with this slide by now. Okay, let's talk about this graph. So this is a position time graph. Let's do what we should do every time you see a graph. Analyze the scale. Right here, y-axis is about position or displacement. It means the same thing. And what does positive mean? So if you were below the x-axis, you would be going backward or downward. Yeah, forward. The opposite of forward would be backward. All right, so you're covering a certain amount of distance in a certain amount of time. Let's take a look at this graph. At the top right, do you see how it starts to curve up here? So what's happening over here? Some non-uniform motion. Here is uniform, and then there's a little bit of curvature right here. So it looks like you speed up for a bit, and then you're pretty much going the same speed for a while, and then you slow to a stop. What would that be like? But eventually it would stop due to a friction, right? If that wall wasn't there, it would eventually slow to a stop, right? So I got to give it a little bit of a push. It speeds up. It pretty much goes the same speed for its journey, and then it slows down at the end. What you can do, you guys, is draw tangent lines. See if you can draw a couple of these. And they just have to be sketches. Flat. Steeper. Okay. So I drew a couple tangent lines at 0 and at about 2. At 0 seconds and 2 seconds. Those slopes are getting steeper in the positive direction, so it's speeding up. Then what starts to happen? It starts to taper off, hey? See, those tangents are becoming flatter. Those tangents are becoming flatter, which means it's slowing. You're becoming less steep. Those tangents are becoming less steep. So jot that in. Tangents become less steep. Tangents become steeper. So that would be speed up. This would be speed down. Okay, so if you get a curved DT graph, don't be afraid, right on the test, just to start sketching tangents. Is this thing speeding up or is this thing speeding down? Which direction am I going? Am I above the x-axis? Am I below the x-axis? Those are some of the questions you can be thinking about as you interpret a graph. I want to finish this lesson up, so how close are we? Not bad, not bad. Okay. Am I good on this slide? All right. So we're going to sketch the AT graph. This is not too difficult of business. We've already talked about it a little bit today. So the graph has some clear distinctions, Mr. Jed. You have up to, what, 3 seconds or 4? 4 seconds, 4 to about 7, and then 7 to 10. So there's some clear distinctions. So make those distinctions for yourself. Got section 1, Section 2 and section 3. Those are very clear. You wouldn't be asked to do this for a curved VT. You would never have that in this class. So it's always going to be linear, so it's not too bad. They want acceleration, and we're sitting at velocity. So how do you go from velocity to acceleration? Find slope. Beautiful. So my zoom is not working. I'll have to figure that out later. But I'm going over 1, 2, 3, 4. And how much did the y change? 1, 2, 3, 4, 5, 6, 7, 8. So delta V is positive 8. And delta T is positive 4. I get positive 2 meters per second square. That is tiny. I apologize for the tiny writing. I should have that fixed by tomorrow. I just don't want to troubleshoot in front of you guys. It's 8 over 4, positive, positive. Are you okay back there? Imre? It's your birthday, I get it, but don't have to make jokes the whole time. Section 2, how about this? Section 2. Again, in 3 seconds, so you've gone from, what is this, 4 to 7? In 3 seconds, okay, so in 3 seconds, how much did the y change? 0. 0 change. The red line changed 0 in 3 seconds. So then you would be, see if I can, I'm going to write a little bit bigger now. For section 2, 0 meters per second in 3 seconds. 0 meters per second square. And for section 3, you drop from 8 all the way to 0. So you go 0, take away 8. And then from what time frame to what time frame? 7 to 10. So obviously it's 3. Okay? 10, take away 7. Negative 8 over 3. 8 over 3, what was that? 2.6 repeating? 2.6 repeating meters per second square. Negative. So slope calculations should be no problem. I've demonstrated it 3 ways, well 2 ways. Just doing a triangle, right? Just doing a triangle, or actually using the formula. And now to graph these, all you need is a straight edge tool. For section I, it's 2. So here's 2. Here's 0. For how many seconds? 1, 2, 3, 4. Then for the next 3 seconds, it's 0. 5, 6, 7. And then for the last 3 seconds, it's negative. And it's a little bit farther down. 8, 9, 10. Went a bit too far. Oh my gosh. I don't want to be lazy. This is a time acceleration. A versus t. Here's negative 3 down here. Because it's the time frame. 0 to 4, you're accelerating at this rate. So it's 0 to 4. 4 to 7, your acceleration is 0. And then 7 to 10, your acceleration is negative. This is 2.6 if that menu wasn't there. Guys feel okay about that? You have to draw it right in there. Maybe make it thick so you can remember where it was. Calculate the displacement for the whole trip. Calculate the distance covered for the whole trip. So now, if we used slope to find acceleration, we use area to find displacement or distance. So the first section of the graph is a triangle. 1/2 BH. 1/2, help me out. B was 4, right? Just trying to remember to the graph. And the height is, it got up to 8, right? 4 times 8, 32, cut that in half. 16 meters. And that displaced positively or negatively? Up above the x-axis or below the x-axis? Oh, yeah, up. Good. Put that in there. What's the next shape? Oh, rectangle. See how easy this is, guys, if you just remember and study? Rectangle. What's the length of that rectangle? 4 to 7, the length is 3. And the height is still 8. LW, 3 by 8, 24 meters. Above or below the x-axis? Above. Next one. What kind of shape is this? Triangle. Base is 3. Height is 8. 1/2 base height. 1/2 3 times 8. Half of 24? 12. Above or below the x-axis? Above. So in this case, the displacement is equal to the distance. Not always going to be that way, but in this case it is. If there was some stuff below the x-axis, that would work against you because now you're traveling away. Okay? So 16 plus 24, help me out, 40. 40 plus 12, 52. Okay. And positive if it's displacement. Is that it? Oh, a couple more. So let's have you guys work for a bit, and we'll come back to this question. I'll let you guys have a look at this. Too much of me at the front. The quiz, it's possible.